Alright folks, a few thoughts before we begin. This is for my honors chem class, looking at worksheet 4, thermodynamics. Quick question, I don't know if you can see this, I'll zoom in a little bit, but this is your supplemental reference table. A couple of things you want to make note of right off the bat. Your temperature is 298 Kelvin. You're also working in kcals per mole. Notice British units here. Well, that's kind of a dead giveaway when you look at the problems on the worksheet. If your units are given British, you know you're using this table. If your worksheet has units that are metric, SI, you're going to be working in kilojoules. And table I actually replaced that previous table. So you'll notice over here, these are just kilojoules. Well, this is written stoichiometrically. This is, for example, in the first one, CH4 plus 2O2 goes to CO2 plus 2H2O. It releases 890.4 kilojoules for every 2 moles of water formed, or for every 1 mole of CO2 formed, or for every 2 moles of oxygen consumed, or 1 mole of methane consumed. So you've got some stoichiometry to contend with there. I'm going to pause this momentarily. The problem that I see from time to time with my honor students with regard to worksheet 4, when they say, see the equation in the supplemental reference table, and it says, for example, in number 1, forms NH3. You're looking for a heat of formation of a compound from its elements. The elements in ammonia are nitrogen and hydrogen. However, they are both diatomic. Well, if I try to balance that equation, I'll see I've got a 3-2 situation here. I put a 2 here and a 3 here. Well, now I'm forming 2 moles. That's not what the numbers in our supplemental reference table are listed as. This is per 1 mole. So if I want to form 1 mole, I would divide everything by 2. Let's get that to cancel. So really, my equation in the left-hand box in your worksheet is 1/2 N2 plus 3/2 H2 goes to NH3. Use of fractional coefficients is fairly rare, but certainly not unheard of. It's something we'll do from time to time, but don't let that throw you too much. This is forming 1 mole of ammonia from its elements. Pause. We're back. We know from previous lessons that our equation that relates the first 2 laws of thermodynamics, girls have true sensitivity, guys have no true sensitivity. Certainly our supplemental table gives us the values for delta G, delta H, and T, and our job is to solve it for delta S. So delta G, let's form 1 mole of ammonia. It says delta G, ammonia, negative 3.9, and those are kcals per mole. Delta H, negative 11.0 kcals per mole, minus 298 Kelvin, that's given in the table at the top, times delta S. I'm going to add the 11 kcals per mole. Handy dandy calculator, but don't let the arithmetic throw you. So we've got positive 7.1 kcals per mole equals negative 298 Kelvin times delta S. Now I'm going to divide out by negative 298 Kelvin. Negative 0.024-ish. You go, well, what are my units? That's where people get confused. So how does this work out? We'll pause that 1 second. Certainly I could write it like that. What I have here is really a fraction in my numerator, and I could express my denominator as a fraction, which would be equivalent to negative 0.024 kcals per mole times 1 over Kelvin, which leads me to negative 0.024 kcals per mole times Kelvin. So your numerator has units of energy, denominator has units of quantity and temperature. All right, it's important that you pay attention to the units in these questions. That's where people tend to go wrong. Looking at these values, we see that we have a negative delta H. That would certainly be an exothermic reaction. This is my potential energy, my enthalpy. This is my reaction coordinate. Now moving down, that's negative delta H. That, as we discussed earlier, was favorable in nature. I also see that I have a negative delta S, losing entropy here. Okay, we said earlier that energy bad, we wanted to get rid of energy. It was favorable to be exothermic. We also said chaos good. Well, if I'm losing chaos, that doesn't strike me as very favorable. So I would describe this as an unfavorable situation. So I've got competing first and second laws of thermodynamics. Delta G is what reconciles the two. The fact that I have a negative delta G tells me, in fact, that this was a spontaneous reaction. If you have sufficient activation energy and you get this reaction started, it will continue by itself. Now, Mr. Bauer advises me that the words spontaneous or not spontaneous have kind of fallen out of favor with the AP, so they would describe this now as overall thermodynamically favorable. Those are the terms for the AP now. Formerly, we'd say it was a spontaneous process or spontaneous reaction.